important. This pins and signals talks about the hardware part of the microprocessor. Hardware part. Okay. So what is the hardware parts? You may feel, what is the hardware parts? See, this is nothing but a microprocessor. Okay. We're talking about data. We're talking about some read. Talking about write. Everything is done by the microprocessor, right? Microprocessor is the brain of a microcomputer. Brain has to do a lot of controls, right? It has to send the signal, it has to receive the signal, okay? It has to receive the data, it has to generate an address, everything is required. That's what we're going to see in this hardware part of the 8086 microprocessor. We have already seen it, okay, during our first introduction chapter. Our first introduction chapter was based on a little bit on the hardware. Then suddenly we have jumped to the software because you have to do the lab experiments. So doing software part in the beginning is important for that. Okay. Okay. You all know that 8086 microprocessor has 20 address lines and it has 16 data lines and all remaining signals are control signals. This is already known to you. We have already explained to you about this. Okay, can you tell me how much memory it can address yourself, my dear? What is your name? Hello? What's your name? Harshit, can you tell me? It has got 20-bit address lines. How much memory it can accommodate? This is the 8086 microprocessor. It has got 20-bit address line. How much memory it can address? You don't know. Huh? At least have some interest in studying. You are inside the class and you are not taking class. If you don't know this, then what else you know? Come on, my dear. Huh? Didn't I teach this to you? Yourself, Harshit. Harshit Bansal, right? Did I teach this to you? There was a question also in this. Did you write that question? This is not a problem with you. Have some interest to study, my dear. All these are very simple things. These are not rocket science. These are very simple things which you need to remember. Okay. Can you tell me how much memory it can address? It can address 2 to the power of 20. 1 megabytes of memory. If the memory is byte addressable. Right? Okay. These are the things we have already seen. And what is this? Tell me. This is a basic microcomputer system. And what you see here is a microprocessor. This is the microprocessor. This is a microprocessor. This is a microprocessor. And you all know that microprocessor has to be interfaced with ROM, a memory, and I/O ports. Okay? So this is an interface. This is a microprocessor. This is a microprocessor. Okay? And this microprocessor inside, it consists of only ALU and some registers. Okay? But you all know that microprocessor has to be interfaced with the memory. Memory can be of two types. One is ROM, read-only memory, and random access memory. It is not that only memory is connected to the microprocessor, you also connect the keyboard, display. It can be a sensor, it can be a motor, it can be servo motor, it can be stepper motor, anything can be interfaced to this 8086 microprocessor. You all know about it. So, how does it do the connection? How the connections are done? Okay, between a microprocessor and a ROM and other things. Okay. And you all know that microprocessor needs an address to locate anything which is outside that. It can be a memory, it can be an IO, anything, right? You can see the memory and IO ports. The memory and IO ports are connected with the address bus. This is the address bus. And I already told you about address bus in my previous class. And I don't want to repeat it once again. Right? See, the address bus is connected to the ROM, RAM and IO ports. Okay. The IO devices, whatever IO devices you are connecting to 8086 microprocessor, it can be a disk, it can be a camera, it can be anything. There are n number of IO devices can be connected. It is connected to the port. There is something called IO port, an external integrated circuits connected to 8086 microprocessor. Right? Okay. Now, address bus is used to locate data from the memory and also used to locate the IO devices. Okay. So, this is what the address bus does. And all the data from the memory or memory to microprocessor or microprocessor to memory, IO to microprocessor, microprocessor to IO, everything is actually carried in a bus called as data bus. All data are going into this. This is the simple architecture of a microprocessor based system. Okay, this is the architecture. If at all you're going to design a microprocessor based system, this is what it looks like. You need to design a proper memory interface and proper IO interface. Okay, this is just a block diagram of a complete microcomputer system, and all should know about the ROM, about the RAM, about IO ports, about address bus, about data bus, and this is the microprocessor which has an ALU and other control unit inside. All these things are already done, and I'm stressing once again, this is very important for the examination. Of examination. Okay, this is what your the actual 8086 microprocessor is. Right? A microprocessor is a digital device. It's an integrated circuit. Okay, it's a hardware chip. Okay, it consists of various pins. It does various operations. Okay, so at present, what you know about microprocessor is it consists of 20 data lines, right? It should consist of 20 data lines. It should consist of 16, sorry, is it 20 data line? 20 address line, 16 data line. Okay, and definitely we have briefly told you about some signals, read signal, write signal and all. Other than that, we don't know anything about the microprocessor, the real hardware concept of that. Okay, now see this. Let us first locate where is your 20-bit address line and 16-bit data line. See, try to understand each and every point. There is only 1 or 2 weeks for your examination. Make use of your classroom effectively. Right? Don't simply spend time on your mobile and spoil yourself. Keep your mobile phone inside. Every class I'm stressing you. Right? It may be force on you, but I do that for your betterment. Okay? Now see here. First we have to locate where is 20-bit address, 16-bit address line. Okay, so can you tell me, suppose if I go for a separate 20-bit address line and 16-bit address line, so 36 pins will go for only this one, right? So each pin can take one bit. Okay, 36 pins should go. Okay, but how many pins it has? It has only 40 pins. Suppose if out of 40, if 36 pins goes for your 20-bit address line and 16-bit data line, only 4 pins are remaining. Can you accommodate all other control signal in the 4 pin? It's not possible. Here comes the concept of multiplexing. Have you heard about multiplexing? What is multiplexing? In DD you must have studied multiplexing, right? So multiplexing means you can use actually one line for multiple purposes. Okay? In the shared fashion, from time to time you can just use it for different purposes. So here, what is done, since 36 pins usage in a integrated circuit, okay, takes all the pins out of 40 pins. If you are planning for 40 pins in integrated circuit, then it's not going to work out. That's why what is done in this is the address data line is multiplexed. Okay, address data line is multiplexed. You can see here some of the pins which is named as, see, AD0, AD1, AD2, AD3, AD4, AD14, and here you have AD15. This data line, this 16-bit data line is also multiplexed with 16-bit address line, right? That means there is a single pin for address line 0 to address line 16, and the same pin you are going to transfer data bits. There is 16-bit data possible in this, D0 to D15, because we are starting from 0, we have to 15. So this is multiplexed. These two are multiplexed. That means microprocessor has to use this particular pin in a shared way. So very carefully it has to use the data line. It will be converted to data line when it wants to transfer data. It will be converted to address line whenever it wants to send an address. Okay, the microprocessor does it. There's some control signal which makes this line to be acted as a data line and also the address line. Okay, we will see that which signal will make this AD0 to AD16 to work as an address line, and at which time which signal makes it to become a data line, right? It is taking a role of both address and data. So there is one signal makes it address, there is another signal makes it as a data. We will see that. Okay, but now what you need to understand that there is only one pin assigned for both address and data. The purpose is to save the pins, right? Otherwise, unnecessarily, your integrated circuit, your microprocessor, which is actually built on integrated circuit, will have 36 pins only for address data. Then what about remaining signals? Remaining signals you need to provide some more pins. Then it will become bulky, right? Your integrated circuit will become very bulky. That's the purpose multiplexing is used in most of the microprocessors. Fine? Okay. Let us see about other pins one by one. So what is important here to understand is address data line. I have told you about address data line. See AD02, see these are pins, AD02, AD15. It is used as both address and data, right? 16-bit data and 16-bit part of the address, but address is once again 20-bit, right? And that is also multiplexed. Can you see here? See, your address, your data is only 16 line. Okay, once it is finished, you can see your 16th, 17th, 18th and 19th address line is also multiplexed with some other status signal. We'll see that. Okay, now, so we have seen about these pins. We have seen about this pin. You know what this does. I'll briefly tell you about what are these pins does. Remember. Now, very important. Power is very important. VCC and ground. Right? VCC and ground. Power is very important. VCC and ground. Just 5 volts Ground? This is ground. You all know about it. Let us see about very important signals. Min max. What is min max? Right. This microprocessor can be operated in two modes, in the minimum mode and a maximum mode. Okay, we'll see what happens when it is operated in min mode, what happens when it is operated in maximum. Okay, see this min max, it's written as min slash max bar. What is the meaning of this? Whenever you give 1 to this, it will operate in a min mode. Whenever you give 0 to that, it will operate in a maximum. That's the way it's represented here. Hope you are understanding this. Okay, we'll see what is min max mode. We'll see. Okay, and very important signal, write signal. See, can you see a write bar signal here? This is the write bar and read bar. Why there is a bar on the top of the signal? Why there is a bar on the top of the read signal here? That means it is active low signal. Suppose microprocessor wants to read something, it will generate a low signal on this, right? Suppose microprocessor wants to read something from the memory, it will generate low on this. Similarly, a microprocessor wants to write something into the memory or onto the I/O devices. Okay, it is once again a low signal. That's why you have the bar on the top of it. I understood this. Okay. Okay, now I have told you about read signal, write signal. Okay. So certain signal which will be very useful for you. See, there is something called ALE here. What is this ALE? I will tell you only important signals. What is ALE? ALE is called as address latch enable. Address latch enable. And what it does? This is the signal which converts your multiplex address data lines, okay, to address line. So whenever the ALE goes high or low depending on the microprocessors, okay, the ALE signal will tell you that the address data line has to be used now as an address line. Whenever ALE goes high, okay, ALE goes high. When ALE goes high, that means your address data line is now acts like a address line. That's called address latch enable. Okay. Similarly, you have another signal called data enable. This is data enable. What this does, tell me? When this signal goes either low or high, or normally it is bar signal means it has to go low, right? Data enable bar. When this signal goes low, what happens? Your address data line, which is actually multiplex address data line, it will become a data. Right? So we have seen about this, we have seen about this, right? We have seen about write signal, we have seen about read signal. There is something called M bar IO, M/IO bar. Okay, M/IO bar. What is this M/IO bar? See, you are connecting not only memory to microprocessor, you are also connecting IO devices, right? Microprocessor reads data either from a memory or from IO devices, right? So by how microprocessor comes to know that it is reading data from memory or IO devices? This signal tells. If this pin has 1, that means microprocessor is doing memory operations, right? If this pin takes a signal of 0, that means your microprocessor does the IO operation. Whatever data coming inside or going outside from the microprocessor is going to be from IO. Okay, so we have also seen this. Fine. We will see about this little later. Okay. And what is this bus high enable? Bus high enable. See, bus high enable. See, this microprocessor has 16-bit data, as or no, right? 16-bit data. Okay. See, it can be divided into two 8 bits data, right? Two 8 bits data. Okay. So whenever you are trying to use entire 16-bit data, okay, entire 16-bit data, you are occupying entire 16-bit data bus. Suppose if you want to take only half of that, you don't want to use the remaining of that, right? You want to take only half of that, only 8 bits of that, because there are a lot of 8-bit operations possible in this, right? If you use a register AX, you also use the register AH and AL, is a two 8 bits, yes or no? You also do that. In such cases, if you want to take the control of the higher data lines, higher bit data lines. What are higher bit data lines? What are the higher bit data lines? Data line is 16 bit, right? Okay, what is higher bit data line and what is lower bit data line? Come on. 0 to 7 is a lower bit, right? And D8 to D15 is going to be higher bits. You know about it. Suppose if you want to take a control of only higher data lines, then you use this bus enable. You make bus enable signal as a 0, right? So that the microprocessor will take care of only the higher bit. Okay. So all these signals which I told you has to be actually seen through a diagram called as state diagram, timing diagram, which we'll see. It's very interesting to see that diagram. Okay. Okay. So this is a brief introduction of pins. There's other pins we'll tell you. There's something called interrupt pin here. Interrupt pin. So interrupt, you have already used interrupt in the lab. That interrupt is different. This interrupt is different. This interrupt is the hardware interrupt. What interrupt you have used in the lab is called software interrupt, right? Suppose if I want to interrupt this microprocessor externally, okay, then you have to send one to this particular pin. Microprocessor will stop doing whatever operation it does, right? Okay, and what it does, it takes the control to the a small set of programs, okay, which is actually which is called an interrupt service routine, okay, which is according to whatever task you interrupted for, right? See why we need to interrupt microprocessor. Suppose imagine that I have connected a sensor. Sensor is suddenly receiving one signal, right? So that signal has to be passed to the microprocessor. Microprocessor may be doing something else during that time. So at that time, sensor will give an interrupt to this microprocessor, say that, hello, I'm going to give a data, you please take it, right? And then giving data means that there is a subroutine. The microprocessor has to execute some other program, what it is compared to what it is doing. Okay, once again, microprocessor has to acknowledge that, then only the sensor can send the data. See, giving acknowledge and giving no acknowledge, it's left to microprocessor. See, you have interrupt here, right? Somewhere you have interrupt acknowledgement. Can you see here? When you interrupt the microprocessor, if you don't want to interrupt, if you disable interrupt, okay, it won't give interrupt enable, right? If you don't disable interrupt, then it will give an acknowledgement saying that you send the data. That's why you have this interrupt and interrupt acknowledgement. There's something called non-maskable interrupt. What is non-maskable interrupt? Non-maskable interrupt means if any signal is coming to this as 1, that means microprocessor has to respond, especially power failure. Whenever there's a power failure, okay, microprocessor has to respond, okay, and give a signal that you try to save your data, there is a power failure. I've understood this, okay? So that is called a non-maskable interrupt. All these details can be taught in a separate chapter called as interrupts. There is a separate chapter called as interrupts. In that chapter, we'll teach you in detail about the interrupts, okay? Now I'm just telling you brief about this, okay? So all the important signals I told you, okay, and this signal sender will be telling whenever we come across with that, okay? Now it's not required, okay? Fine. Okay, I told you there are two types of operations. You have min-max pin. You have seen min-max pin in a microprocessor. So min-max pin, it will set your microprocessor to either work in the minimum mode or in the maximum mode. Okay. Normally it is used for minimum mode only. See, whenever you give 1, it will work in the minimum mode. In minimum mode, how it works? In minimum mode, it works as a single microprocessor system. Okay, it works in a single microprocessor system. There's only one microprocessor works. It's a we can say it's a microcomputer system with a one microprocessor, nothing else. Okay, so it is suitable for smaller system. It is cheaper. In max mode, okay. So how does it work in a max mode? Okay, in max mode, okay. See, your microprocessor has always some limited capability, right? Especially when it comes to math operation. Okay, when it comes to math operations, floating point operations, microprocessor needs somebody else to help, right? At that time, you have to connect one coprocessor along with the 8086 microprocessor, right? But coprocessors are available. So if at all you want to connect a coprocessor to microprocessor so as to do a larger math operations, okay, at that time you have to operate that microprocessor, 8086 microprocessor, in the maximum. That time only you have to operate in the maximum. Otherwise it is not. So have you understood this min-max mode? Okay, but in this syllabus, most of the time you will be studying about only minimum mode. You are not going to maximum mode. We are not going to study about the coprocessors and all. Okay, fine. So this is about min-max mode, and okay. So hope you understood about pin diagrams, right? All the pins you understood what exactly it does. We will see its operations one by one now. Okay, fine. What are the pins we have discussed now? Address data line multiplexed, yes or no? Okay, we saw about read pin, write pin, right? We saw about other pins such as address latch enable, data enable. We saw about interrupt acknowledgement. All these things we have seen, right? All these are pins. Okay. Now, let us see three important terms of this microprocessor execution. Okay. There is something called instruction cycle. What is instruction cycle? Okay. See, time taken by 8086 microprocessor, okay, to complete execution of an instruction is called an instruction cycle. Right? Can you tell me what are the different phases of this instruction execution? We have seen it in the first chapter. Fetch, decode, and execution. Yes or no? Very good. Some of you remember it. Okay. The time taken to fetch, taken to decode, taken to execute, all together is called as complete instruction cycle. I understood this. Okay, that's called instruction cycle. What is machine cycle? Machine cycle is something. Suppose you have instruction fetch, right? Instruction fetch, data write, data read. All these are called machine cycle. Okay, the time taken to fetch an instruction or to read a data from the memory or to write data into the memory. Right? It's called machine cycle. See, your instruction cycle can have multiple machine cycles. Yes or no? Right? Your instruction cycle may have multiple machine cycles. You know, your instruction cycle is time taken by the instruction to fetch the instruction from the memory if plus if at all there is any data transfer from memory to microprocessor or microprocessor to memory, that is also considered to be part of instruction cycle. Okay, so each instruction fetch, data read, and data write, all these are called as machine cycles. Machine cycles. I have understood now. Okay, data read is one cycle, one machine cycle. Data write is another machine cycle. Instruction fetch is also a machine cycle. I have understood this. Okay, so that is called machine cycle. Have you understood about machine cycle now? Have you understood about instruction cycle?
So you said it's time taken to like complete a set of instructions.
Okay. Instruction cycle is time taken by the microprocessor to complete execution of an instruction. One instruction. And that one instruction can take multiple machine cycles. And what is the machine cycle? Machine cycle is a time taken by microprocessor to fetch an instruction, or time taken to write data into the memory, time taken to read the data from the memory. Everything is one machine cycle. I understood this. So hope you understood when I said your instruction cycle will have multiple machine cycles. I understood this because a particular instruction, if you take this instruction, right? First, there is an instruction fetch, right? There's an instruction fetch. The instruction fetch depends on the length of the instruction. The instruction fetch depends on the length of the instruction. Yes or no? Right? Now, similarly, can you see this instruction also have to read data from the memory? Right? It has to read the data from the memory, right? From the offset 0114. It is also then copying the data to the BX register. It does multiple work, and that each work takes a machine cycle, and that is contributes to a total instruction cycle. Right? So taking this instruction, see, you have this instruction move BX comma in the bracket 0114. I want to ask a question to you now. What type of addressing mode is this? Come on. What type of addressing mode is this? Forgot. Huh? What type of addressing mode?
Direct.
How many say direct? Remaining people doesn't know? What? What type of addressing mode? Huh? Is it indirect? Then what you do in the class, my dear? You have done so much of. Huh? This is the direct addressing mode. You are putting the address directly here in the within the square bracket. How many times I told you this? So what it does, it copies the content of the memory to the BX register, 16-bit content to BX register, right? So now when this is executed, first cycle will be your fetch cycle, instruction fetch. It takes one machine cycle for that. Similarly, then the execution, decode and execution, that it takes the data from the memory and put it back to the BX register. Understood this? So now it takes two machine cycles. We'll see that how much machine cycle it is going to take. Have you understood about this machine cycle and instruction cycle? What is T states? T states is nothing but a clock signal. It's a frequency of the clock, right? You all know that. I think I forgot to tell you, this microprocessor has to be connected to the clock. Clock signal is very important for this. Can you see here? This is a digital system. This digital system requires clock. right? So that means every instruction will be executed based on the clock speed, right? So now you can see normally clock is written like this. Okay, so now if you see distance from this here to here is one t state. Okay, distance from here to here is one t state. Similarly, distance from here to here is another t states. Accordingly, your microprocessor signals will be changing. The pins in the microprocessor, the signal level of the microprocessor will be changing. Okay, this is called t states, each t states. You understand about the t states now. Okay, most of the time you have seen the clock is written like this. Most of the time you have seen the clock is written like this. Okay, you must have seen it is written like this in the lab. Okay, but it can also be represented because practical clock signals are not having exactly the sharp edges here. The practical clock signals are not, you've already seen that. Okay, you know about it. Okay. So clock signal, how do you give clock signal to the microprocessor? The clock is generated from a crystal controlled clock sent to the 8086 microprocessor. One cycle of this clock is called as T state. It's called T state. The state is measured as a falling edge of the one clock pulse to the falling edge of the next clock pulse. Understood this? Okay. This is where it can be rising to rising, doesn't matter, or falling to falling, doesn't matter. That will be, it's going to be same. It's going to be same T. Okay. Okay. Once again, different versions of microprocessor will have different frequencies. Okay. It can be anything from 5 megahertz to 10 megahertz. Okay. The minimum time of one state will be between 100 nanoseconds to 200 nanoseconds. How do you get this? Can you tell me? How do I get 100 nanoseconds, 200 nanoseconds? This one upon this one upon, that's all. Right? You all know about it. Okay? The basic operations such as reading a byte from memory or port, writing a byte to memory or port is called as machine cycle. One machine cycle is something is the time taken by the microprocessor to read a byte from the memory or port, or write a byte to a memory or port. What is instruction fetch? Tell me. What is instruction fetch? It is like getting that instruction from the memory, right? Once again, it is reading from the memory only, right? So machine cycle is time taken by microprocessor to write the data into the memory, read data from the memory. It's called machine cycle. Now we have to see how much time a particular instruction takes to complete the execution. That's what we are going to see now, right? So if you have understood about what is instruction cycle, what is machine cycle, what is T states, let us go to one by one and see how it is calculated. Before that, about clock signal. See, a clock is generated by a chip called as 8284. It's a separate external chip, right? The clock signal you have seen in laboratory that the clock signal is separately coming from some other place, right? You put a wire into the clock, that means it is generated there inside the key trainer chip. It is generated. Okay, so a crystal oscillator is connected. This is not much, you need not buy at this. It is generating two clock signals. One is 5 megahertz and 2.5 megahertz. Okay, microprocessor can use any one of this. Suppose if it wants to use both, it can use, but it has got only one clock pin. This can be connected to the clock signal, and this is called as clock circuit. Clock circuit. Okay, machine cycle. Let us come to machine cycle now, because this is very important for us to know. See, I told you that a machine cycle either memory read or memory write. One machine cycle is one memory read or one memory write. Memory read, it can be a reading an opcode, it can be reading a data. Yes or no? Right? But memory write, are you going to put the opcode into the memory? No. You are putting only the data into the memory. Similarly, you have IO read and IO write. Something you are reading from the IO devices and something you are writing into the IO devices. It requires a separate machine cycle. That is what is machine cycle. Now let us see how do you calculate a machine cycle for this. Right? See here. You have an instruction move AX comma BX. Right? Move AX comma BX. Okay. Now, what is this? This is the opcode, machine code. Okay, this is what's stored in the memory when you write a program. Right? Okay. Now, what it does? This particular instruction, it requires only fetching. That's all. It doesn't have any memory read, memory write. That's all. No. This doesn't have any memory read, memory write. Whether this instruction has got anything like memory read and memory write? No. What it does, moment the instruction is actually fetched from the memory and microprocessor actually decodes it, everything does it in one machine cycle, and in that machine cycle it actually transfers the content of the BX register to AX register. But it doesn't require any extra machine cycle to get the data from the memory or put the data into the memory. It doesn't require this or no? Does it require any extra machine cycles? No. So in that case, can you tell me now what is the number of machine cycles required to execute this instruction? Only one. Only one. Have you understood now why only one machine cycle is required? Because there is only instruction fetch involved in that, in this, nothing else. That's why to execute this instruction, you require how many machine cycles? Only one machine cycle. That also for opcode fetch. Opcode fetch. Remember this. It's very important. Okay. Now I'll go to some other instruction now. Now can you tell me this? Okay, can you tell me now how much machine cycle this requires? Is very tricky here. See, microprocessor can at a time can read only 16-bit data, you know, right? In one machine cycle. Okay. Now this is the instruction. Listen carefully. All of you listen carefully. Okay. Here only you can understand the facts. If you don't concentrate, you will never able to understand this. Many people I can observe that then somewhere else. Okay, don't do that. It's very easy to understand. Right? Okay? A small kid of first standard can understand this. See, this is the instruction. What this instruction does? It adds content of BX register and content of the memory whose offset is 0110 and puts the result back to BX. Right? Now, when we write the machine code for that, it is coming to be 031E1001. Now, can you tell me how many machine cycles your microprocessor require to read this instruction? Does it read by one machine cycle? Why? Because it is not, it is actually, this is 16. It requires two machine cycles. It requires two machine cycles to read the instruction fetch. Right? Okay. Now, you know now that To fetch an instruction, this instruction takes 2 machine cycles. Okay, keep it. Plus, is there any extra machine cycle required? What is that? You are reading data from the memory. You are reading data from the memory. Since you are reading data from the memory, you require 1 more machine cycle. 1 more machine cycle. So plus 1. So how many machine cycle does it require? 3. You just have to remember that whatever the times, number of times it takes the data from the memory and puts the data into the memory, everything is 1 machine cycle only. So this instruction has got now 32-bit, totally is 32-bit, yes or no? This is 16, this is 16, right? Microprocessor cannot read this entire 32-bit at a time. Microprocessor has to read this first 3031E in 1 machine cycle. It will read this 1001 in the another machine cycle. So it takes 2 machine cycles to read the instruction, to fetch the opcode from the memory. Okay, so already 2 machine cycle you got. Then check, is there any data transfer? Either read or write. Yes, see here, it is reading the data from the memory. Right? It's reading the data from the memory. That means there is 1 more memory read cycle. 1 more memory read cycle. See, reading data from the memory. So what is the total number of machine cycle? For this, 3 machine cycles. The total number of machine cycle required is 3 machine cycles. This is the way you have to calculate the number of machine cycles required to execute an instructions. Right? So can we do it for many instructions here? This takes how many machine cycles? I've understood this. Each machine cycle may take 4 or 5 T states. Try to understand this. Right? Each machine cycle can take 4 or 5 T states. Right? So accordingly you can calculate, if I give the clock speed, you can calculate the amount of time required to execute a particular instruction, which we will do it in the next class. This is very easy. Don't miss any of the classes. You can really score well. Okay, if you don't want, if you feel that you are okay with whatever you want to do it, doesn't matter. Okay, but my suggestion is you come to the class and study this. This is very important. You can just get it done in the class only. There's nothing that you need to remember in this. Right? Have you understood what I said today? Right? I told you about machine cycle, I told you about instruction cycle, right? And I told you how to calculate the machine cycles, right? Similarly, can you tell me how many machine cycles this requires? I want you to, it's already there, okay? But you tell me how many required there. Why there are 4 in this? I want somebody to tell me. Of course, it is getting the data from the memory, and also it is putting data into the memory only. So you have 2 cycles for opcode fetch. Of course, this is your opcode machine code. You require 2 here. You require 2 machine cycle here. And there is 1 machine cycle to get one of the data from the memory itself. And after adding, it is putting data back to the memory. 1 more data set, or 1 more machine cycle. So totally you require how many machine cycles? Come on, 4 machine cycles. Try to understand it. This is very important. Questions are going to come on this. And it's very easy. 100%. You know, first standard, present first standard students can do it.
Yeah. If there is violation or segment overriding,
Everything you see, suppose if there is a violation, you have 67, 66. How many machine cycles required now to read the opcode? 3. That's all. It all depends on how big your instruction is. Understood now? Okay? I think I can give you some more examples. I have it here. See this one. It requires only 1 machine cycle. Yes or no? Right? It requires only 1 machine cycle. See this one. I have understood this. There's only 1 memory read. already told you about this. I already told you about multiplexing here. All this hardware I will tell you in the next class.